This is Classical Control Robotics Fundamentals Episode 1. So we'll be covering system modeling. And we'll be covering all these points. But before that, what is system modeling? It is an encapsulation of real world dynamics. And what do I mean by that? Well, for example, you have a crane that you want to make. So you make free body diagram and you get its equations mathematically, and basically in that sense you have its model. So you don't really need the crane to be there to know what it can do. And that's the essentials of system modeling, is that you can simulate your system, and that can be done in various ways: Python, MATLAB, more Simulink. So you can basically just understand what the system will do without fully making the whole thing and applying it. Now this will be more for episode 2, but essentially it's just the general controls, controller and techniques that will be covered. Now in the modeling, you need to know what is time variance. And essentially it's just that a delay in the input is reflected in the delay at output. So the relationship between the input and output is not affected by time, in the sense that there won't be any mismatches or whatnot. But of course, it is affected in the sense that, if you're gonna put a delay, there'll be a delay, but there's no mismatch basically. And models can be linear and nonlinear. And I'll just quickly let you know what is linear and then extrapolate afterwards. But basically, it follows the principle of superposition. So first law is additivity. So you get two inputs, and you feed them through the same system. And you basically, if you add the outputs, it's gonna be the same as if you would take the inputs themselves and add them before putting it into the system. You will basically get the same: y1 plus y2, y1 plus y2. And then we have the law of homogeneity, and that just means that our constant is simply maintained. So you put the constant in the input, you basically get at the output. If you just apply the constant at the output, you would get it KYT, and here also KYT. So it's basically just maintained. And in a very simplistic kind of way, simply if you actuate it, and actuate is like an engineering term, but basically in simple terms, actuation means to do something to the system. So if you do something to the system, you would basically get a line, kind of. It'll have a line shape, as in the sense linearization. So all world phenomena, unless you make drastic simplifications of frictionless surface in a vacuum and whatnot. And one thing, when you're trying to mechanically get a system, if you just use equations that are innately linear to begin with, if you already just assumed the motion of whatever that's moving is F equal ma without any sine or cosine dandy business, then you're basically good. There's no, you basically just don't have to think about linearization because it's already linear. And if you do find nonlinearity and you model it within the equation,
Why would you want that to be linear? And it's specific to kind of the variety of controllers that you get in the linear sense. But you also have to remember that they're only viable unless you kind of have an operation point. So if you're okay with, for example, your nonlinear crane system operating at a 0 point, and you've linearized those equations, so you're using a linear controller for a nonlinear system, but you linearized your equations to be at that 0 point. So for the most part, you'll be okay, since that your point of interest is 0 and it'll just operate around 0. Although I do have to mention that the further you do get away from 0, the more likely it's not going to reflect how it is actually gonna act. So there will be a linearization error. And also, yeah, you get the benefit of the stability analysis that you get from the linear techniques as well, such as, actually I'll get onto that later, but so yeah, basically it's just when you have a point of interest and you want to use the wide array of knowledge around linear systems, controllers, analysis. When you wouldn't want to really linearize is when you kind of want to operate on a wide kind of range. You want your system to at one point be at 0 degrees, then 360, then 180, then 190, just various kind of reference points. So you definitely would probably be better off looking into a nonlinear controller, unless maybe your linearization error is very slow anyway. But yeah, a lot of this stuff about linearization error is definitely seen within simulations itself. But I guess this is the sort of general guideline that within control that it is followed, right? In classical control, you deal with transfer functions, and to make them, you need to do the Laplace transform seen over here. And essentially, this S over here is not this right now, but after the transformation, you will get variables of S. You will get variable S here and there, and they would signify exponential growth decay as a sort of magnitudinal way. And we would have like frequencies as well. So transfer functions themselves, they're linear time invariant. And when we circle back to what I've talked about before, time variant, its relationship is maintained without time doing any funny business. And it follows the law of additivity, homogeneity. So that's what we mean by linear and time invariant. It is single input, single output form. So in and out basically systems. And a lot of systems are just represented by mechanical ODE. A lot of mechanical systems are seen as a form of differential equations, and that simply means that you have equations or a system of equations, and they are in the form of derivatives. That's what we mean by ODE. So why would we want to make a transfer function in the first place if we already have these equations? Well, because when things are in Laplace domain, we get specific insight. And when we put the output y on top and the input x on the bottom of this fraction, we can get what you call a transfer function, an input-output system. And it gives you specific insight in terms of stability. Sort of the step impulse ramp response, the
pole locations in the pole zero map, but I'll talk about this in a moment. First, I want to actually actually, before I go any further, I want you to write some things down. So let's kind of give an example for the most simplistic ODE ever, F equal ma. Now, why is this an ODE? Well, because acceleration is the derivative of velocity and the double derivative of position. So you can write F equal ma to the left of your paper, and under it write F equal mx double dot. We use in control usually, or in general, the notation using dots on top, but there are different forms of notation, but this is kind of the most common, I guess. And to the right, I'm going to give you the general form of how would you do Laplace transforms in general. So to the right, write x as a function of t. What you do is Laplace transform. It will become x as a function of s. Simple enough. Now, when it's x dot Laplace transform, it x dot as a function of time, it'll become s x as a function of s. So what you can see is that when you multiply something with s in the Laplace domain, you can see that in time domain it is as shown as a derivative. So intuitively, what do you think x double dot as a function of time will be? Well, yes, it is s squared x as a function of s. And yeah, that's quite good. And then the last two tidbits for doing Laplace on ordinary differential equations is that when you actually multiply something with 1 over s, so the reciprocal of s, that would be integration in time domain. And when you want to make the Laplace of just a constant, yeah, it's going to be the constant over s. That's simply how Laplace transform works. And so let's do that. Let's do what we have written to the side on our equation. We have f equal ma x double dot. So what do we get? Well, you see what I talked when I said ODE, right? This is actually a system. And actually, before I lose you, f equal ma, it's a system. What kind of system? Well, for example, you got a frictionless surface hockey puck. You push it with your hand, and what do you get? You get f equal ma. Is in a very simplistic terms. So, in transfer function terms, what would our output be? It would be, well, it can be many things, but for us, let's say it's position, right? And pushing it is the force, which is the input. And so let's take the Laplace transform of this ODE. So we have f as a function of s equal m. M is just a constant, it's just mass. We don't do anything with it. And then we get s squared x as a function of s. So, move things around, then you get the transfer function, where in the slide you can see that y is the output and x is the input. So what we would get when we put xs on top and then f of s on the bottom, that would be our transfer function h of s, which would be also equal to 1 over m s squared, right? So that's our transfer function. And if you done it on the paper, congratulations, you've made your transfer function. And intuitively, you can kind of tell what is going on from what I've said before as an integration. So double integration is going on, right? And yeah, you can kind of tell, but you don't get it exactly, right? And that's because when you operate a transfer function, you give it an input. So what would be the input of 1 over ms squared? That's right, it's the force. So, and how does it work here? In transfer functions, it's just you multiply your input onto the transfer function. And what would that be? So that would be f over ms squared. And if you look back to the top of the first thing that you wrote, what would be f over m? That's right, it's acceleration. What is 1 over s? Integration. What would 1 over s squared be? Double integration. So acceleration double integrated is what? That's right, it's position. So, yeah. Now onto a more bigger example, but you see, all the relevant terms are really just the ones that are kind of related to time. And in this example, I'll also do some linearization. So here we have theta t, theta double dot t, theta dot t, and then we have this theta t here, and voltage, which is also a function of time. And this is actually a pendulum setup and connected to a motor, basically. And what do we have here when you see in the red box, which you probably first saw slide? And that's basically just the nonlinear term, right? And since we want to do linear control and use linear control techniques, and we have a certain operating range in mind, we do the Taylor series up to the first term. So here it's seen by with my mouse showing here. So the nonlinear term, we would equate f of x to sine theta t, and x itself would be theta t. And a, although I put here ref, but essentially what it means is that where would we want our system to work around? You know, the A should kind of be the most ideal point at which you want your system to be. And the thing with linearizing is that when you get further away from this point, you will be less accurate compared to the nonlinear system here, or the real system itself, which is nonlinear. But if you're around operating point, which is 0 here in this example, then that's okay. So we do it. We replace our terms. And essentially, the sine theta t will just become theta t. And I'm not saying theta mt because the subscript is not really relevant to this example, what I'm trying to say. So what happened is that this nonlinear term sine theta t just became theta t. So it's not mgr sine theta t, it's just now mgr theta. And so we apply the Laplace transform of the equivalent equation, and I forgot to put r here, but there's basically an r, alright? But yeah, so applying the Laplace transform, we do it here. So what we get, theta s, s theta s, and then s double dot theta s, and all the other terms are just coefficients. They're just some properties of the system that you'll have to figure out on your own. And after that, also, yeah, VAS, you do the fractional form, right, of input and output. and here our output is the angular position, the degrees, or I think it was radians. I'm not sure. I don't remember. But most relevant detail is that we were able to get our transfer function, and also finding the coefficients themselves, whether it's experimentally or whatnot. But essentially, we get our transfer function, and if we would equivalently just want the speed, angular speed, or velocity, let's say, you would just kind of at the numerator multiply by s. And here it's a green box just because I made a small mistake here. But essentially it will be of power 2. And an engineering kind of lingo is transfer functions have orders. So the order here would be 2, since the most highest exponential term here is s squared, so it would be order 2, and if it was x cubed, then it would be order 3. And also more engineering lingo stuff is open loop, closed loop, and what do they mean? Closed loop for classical control is just taking the output and feeding it back. Over here, you can see that. You got the output and you make it the input. The output becomes the input. In open loop, you just have an output, or you put an input and have an output. And you may have looked also towards this, and this is just a lot of the controller setups, right? They don't directly take the output, but also generate kind of an error signal towards our reference, our idealized place of where our system would be. And so we would take the output, we would compare it to where we would want it to be. We are generating an error signal, and it's going into our system. But usually, actually, here we would put a controller, process the error, and then it goes into our system. But it's considered a closed loop system, closed loop control. But of course, there's no controller, so it's just a closed loop system, like this and like that. Okay, now on to stability in general after we get transfer function. And this is something, you wouldn't be able to do if you just had the differential equation. And not to make it daunting, just focus on what's on the left. And basically, when we have the denominator of our transfer function and we equate it to 0, right, we would solve this equation, and we would get 2 poles, -3 for j, complex number, and -3 minus for j. And putting it on a plot would look like this. This is called a pole 0 map. And what a 0 is making equating our numerator to 0. But since we don't have an s, and first I just want to focus on poles in general. So we put them on the plot, right? And we get something like this. Now, just based on this plot, what you can tell without knowing just some simplistic things is that because here's our imaginary axis, this vertical line, right? And this is called the real axis. In regards to stability in particular, we have to focus on the dominant poles relative to the imaginary axis. The dominant poles are the poles that are most right in the whole map. Here, in our example, these are the dominant poles. And since they're to the left of the imaginary axis, the system would be considered stable, meaning the system would decay to 0 in infinite time, or just go to 0 in infinite time. And when we consider the poles, the dominant poles on the imaginary axis,
then the system will not decay to zero, but it will not go to infinity either. It'll just stay stagnant, either with or without frequency. And considering the poles, if they were to the right of the imaginary axis, the dominant poles, then the system would actually go to infinity over infinite time.
Well, what would that all even mean? I will quickly kind of bring you towards general inputs that are kind of used to gauge how a system acts in control, and that's a step, impulse, and ramp input. And really, the graphs speak for themselves. What a step is you just continue to give a signal after some time or initially, and a impulse is just one time just go up to a certain signal level instantaneously. And ramp is linearly just increasing, just by its name, you can tell. So if I bring your attention to this plot here, right, you can tell now how kind of your system would act based on some input that I have shown, or the following inputs that I've shown here. But specifically here, it's based on impulse. So just boom, one time to your system. And for example, this system with these two poles, right here, it would kind of oscillate a little bit and then go down. Because now, why would it oscillate? Because we have this frequency terms here, 4 plus minus 4, and it would go to 0 because it has the term minus 3. Okay, if it would be plus 3, it would actually oscillate to infinity, up and down into infinity. And if you would have no sort of frequency terms, it would just be on the real axis itself. So either exponentially just go to 0, or it would exponentially go to plus minus infinity. And I will also give you a small kind of not too relevant detail, but sometimes it might be talked about. And they're basically time domain equivalent solutions to the system, and they are in the form of exponentials, and you can kind of see how that solution would look like based on thinking in terms of impulse and step responses. But this is just a very kind of nuanced detail that sometimes professors may talk about here and there. But on to the next point is Mason's rule, and I won't get into it too much yet because this I'll get into a little more, and this is not even the complete Mason's rule that's being shown here, but basically sort of block diagrams with loops kind of just can be simplified into one whole system itself. So all sort of feedbacks can just be one system itself, even with the controller involved. It's just gonna basically represent one new other system. But I will talk about its relevance a little later. Now, just a small touch up on control, since we've already kind of gone into modeling a little bit and sort of slightly introduce control in general. And also by the end I'll talk about discretization as well, and talk about the Z domain and Z transform. But a slight kind of deviation from system modeling is just how would you even envision controllers themselves? And they're basically kind of systems themselves. They get an input and they have an output, and that output also goes to another system, which would be our real system that we are emulating, a crane, a chemical plant, whatever. And here's basically the open loop, as I've talked about before, and this is a closed loop. And it has a controller. So you would consider this a closed loop controller. And you have a reference here, which basically is the idealized position of where your system would want, where you would want it to be. Basically, we have the reference here, and we take the output of our transfer function and we generate an error, and the controller controls it to get to the idealized position of this reference. And I put sensor here because in reality we wouldn't be using a model, we would have a sensor sensing where our system is at right now. Although there are kind of techniques that are sensorless operations of systems using estimations and that use models, but normally, for what you need to know now, is that normally a system would have some sort of sensor operating, and then the control will take the feedback, right? It's taking the feedback signal, the error signal, and then it creates another signal to tell how the system should move to minimize the error, usually. Okay, so now on to a small touch up on discretization, and then I'll go on to how a real system may look like. You know, initially how controller's theory would be derived, and controllers in general from the past, they have been continuous. A lot of the theory has been continuous, and the initial application was even continuous, where the controller itself was designed as an electrical circuit with manual tuning knobs. But nowadays, yeah, a lot of control paradigms are now computers. It can be applied in a microcontroller, in a computer, and whatnot. And those have clocks, and these clocks have basically a sampling period, so they're not continuous operation in time. You know, when you go to a shop to buy a new laptop, you can see, oh, this i5 has a something gigahertz. So essentially this is what I'm kind of talking about. So essentially what a real system would look like operating on a digital controller, we will have an output in analog domain, so it's continuous, and then we also have a sensor that's discretizing. So not only we have a controller that is operating on a clock which is innately discrete, but also we have a sensor that's sampling the analog signal with an analog to digital converter. So actually these two boxes are one. That's gonna be the full sensor. I just wanted to stress that there's an analog to digital converter. So essentially the output is now discretized, so it has a K symbol here instead of a T, and it goes into the controller. And depending on your actuator, so what moves the system, what changes it, you might want to also make your output signal from the controller analog as well. Here I gave an example of PWM, and basically also the digital to analog and the controller itself are in one, two, and there are many sort of PWM generation functions, but essentially there is a time domain going on in real life, and then in the more digital side there's a discrete domain. And now I'll discuss what is the Z transform and the Z domain instead of the Laplace transform and the S domain. So there's an equivalent sort of paradigm for discrete systems. So instead of getting xt directly in simulations, you can get xk. But usually the discretization caused from sensors is not really that big of a deal. So, but you see, what the controller will actually take in is its own limiting discretization. So I want to pinpoint, basically, in my experience, the limiting discretization usually comes from the controller. But if it comes from the sensor, that's also fine. It's just what discretization your controller will use. And that's what you will have to look at when you're doing the Z transform, when you want to see the discrete dynamics. So now onto the Z transform, the discrete equivalent of the Laplace transform, the S-plane. And I won't go into too much detail, but basically now we are dealing in discrete samples rather than continuous time. And when you apply the Z transform, you get basically this sort of plot. And the difference between the pole zero plot and the plot that you see now is that the imaginary axis basically becomes a circle. You could think of it in that way, in the sense that any poles outside of it, any dominant poles outside of it will signify that the system is unstable, and if it's on it, then it's marginally stable, and if it's inside, then it's stable. So now our system is actually stable within this plot. And that's basically the majority part that you need to understand. And the reason why we employ the Z transform is that the system dynamics actually changes depending on the discretization. Usually when the discretization is very very small, in the sense that the sampling rate is very high, so it's basically almost an emulation of continuous time, so you won't really see a big difference between the Z transform and the Laplace domain in the Laplace transform. But once the sampling rate becomes slower and slower, you do see more and more different dynamics prevalent, in the sense that you can even turn your system unstable when before it was stable. So this is kind of just an extra analysis that can be done after a discretization.